everything we knew about the solar system just 50 years ago. We got primarily from the back end of a telescope or from meteorites that fell. And when the meteorites fell and we wanted to know where they came from and what their composition was, this mission will make enormous strides answering so many questions that have come up in those 50 years.
Osiris Rex is a mission in NASA's New Frontiers program designed to rendezvous with a near-Earth asteroid named Bennu, survey it in great detail, select a location on the surface to send the spacecraft down to collect 60 grams or more of sample for return to Earth for analysis in our laboratories.
The challenge of finding a tag site on Bennu that met our original criteria was very hard.
But quite honestly, this team thrives on challenge. So even though we knew we had work to go, I never doubted for a moment we would solve that puzzle, that we would crack that nut and we would safely get the spacecraft down to the surface. We had kind of expected the unexpected. This team was ready to be surprised.
3, 2, 1. And liftoff, Osiris Rex.
And we are live here at Lockheed Martin in Littleton, Colorado for a truly historic event. In just a few moments from now, NASA's Osiris Rex spacecraft is going to actually arrive at the asteroid Bennu.
Yeah, so today is what we call arrival. So when we reach 20 kilometers from the asteroid, what we're going to do is do a burn to put us into the precision flying regime that we'll be doing for the next year and a half or so in order to map and discover all we can about Osiris Rex and determine the best possible place to go get a sample of the asteroid and bring it back.
A little nervous, a little excited. I mean, after this burn is completed, we're going to be approximately 7 kilometers away from Bennu at the closest approach. So it's exciting, a little intimidating. There's a lot of feelings going through me right now.
It's going to be the first U.S. mission to return a sample from an asteroid. And in fact, this is going to be the largest sample return since the Apollo program brought back the moon rocks.
This is NASA's first asteroid sample return mission. NASA has had other sample return missions, most famously the Apollo program, which brought back over 300 kilograms of lunar material, which we're still analyzing today to unravel the history of the moon and the Earth-Moon system and the origin of our solar system. But there's been nothing like Osiris Rex in NASA's repertoire. I like to call it the daredevil spacecraft, right? We just zipped around this asteroid like a hummingbird. And it's one of the things the microgravity environment does for you, is that you can stop, you can start, you can turn left, you can turn right, you can go into orbit, you can leave orbit. You really can explore the entire near-Earth asteroid environment in exquisite detail with ultra-precision maneuvers on the spacecraft.
Bennu is about half a kilometer across, the size of a mountain. We're going to be mapping this entirely new, unexplored area of the solar system. So it's been a relatively long journey, as I mentioned, about 2 years to get out to this asteroid. So to give you a sense of a little bit of the mission timeline, Osiris Rex was launched on September 8th, 2016. And one of the first things we did was we did a flyby of the Earth to boost us into the right orbit to encounter the asteroid. So you see that here. We were also able to test our cameras and take a wonderful picture of the Earth as well. Today we arrive at the asteroid and we begin a 1.5-year program to scan and study the asteroid, eventually finding a location in the summer of 2020 to touch down and acquire the sample. The sample, once acquired, is going to be put into a canister and it's actually going to be returned to Earth. You see here Tag Sam putting the sample into this canister, and then in the year 2023, September 24th, this will parachute through and actually land on the Utah desert. So what we're going to do now is actually go into the mission support area here at Lockheed Martin. So how much time do we have now?
It looks like we have about 40 seconds or so before we start seeing the actual burn.
So just to remind you that we're live here at Lockheed Martin and we are just about to arrive at the asteroid Bennu and begin proximity operations to study this asteroid, eventually returning a sample back to Earth.
Yeah, it's so exciting. I can't believe we're here. We're right there. All stations, stand by. Burn has started. Stand by for Bennu arrival. So you can see here we have the Doppler residual, so we know the burn is occurring because I'm seeing a change in velocity from the spacecraft.
It's getting very quiet in here. Everyone's whispering.
We have arrived.
You may have noticed we were doing a bit of an unusual high five there. That's called the tag five, because that's reminiscent of the tag SAM arm that's eventually going to retrieve a sample.
So we are here. We have arrived at Bennu. Arrival was officially December 3rd of 2018, and that was a morning I woke up and saw an event on my calendar that I put there a decade ago. So it was truly a great day for us. Arrival is one of the greatest moments of my career. I remember the very first images that came in, and we had been targeting this asteroid since 2005, so over 13 years of planning and plotting and dreaming about this asteroid, and we first saw it just as a tiny point of light moving across the background star field. And if you didn't know what you were looking at, you would never have spotted the asteroid because it looked like just any other star. But we all knew exactly where to look in that image, and then as you started to blink and we saw this thing move across, and I will never forget that feeling. It's like, it's real. It's really there. There really is something in space, and we know where it is, and we're on our path to rendezvous with it.
The Osiris Rex spacecraft has been navigating around Bennu for about the last 2 years, studying it in great detail, and also overcoming a number of challenges that Bennu has presented. We were looking for locations on Bennu that were 50 meters in diameter, relatively flat, and covered with fine-grained material. And by fine-grained material, I mean stuff that's the size of a dime or smaller.
As we started to approach Bennu from a distance and it started to fill up the camera field of view, it looked exactly like we thought it would, with a few boulders sticking out. But as we got closer, we expected to see a very sandy surface with maybe a few boulders here and there. And what we saw is very little sand. And we saw these mountains, we saw boulders, we saw rocks, and we saw very few areas that had this sandy surface that we were expecting and what we had designed to.
Well, I like to call Bennu the trickster asteroid. So when we first picked the target, we performed an extensive ground and space-based telescopic campaign to try to understand the nature of the surface. And based on thermal data and radar data and the shape of the asteroid, we convinced ourselves that the surface was composed of fine-grained, sandy, or at worst gravelly-like material. And we expected, and quite honestly sold it to NASA as easy to sample. When we got to the asteroid, we realized that the surface was rough and rugged and covered in giant boulders with nary a beach in sight. And we knew we were in for a real challenge. And we not only had to come up with a new way to get to the surface, but we had to ensure that it would fit within a really tight spot and remain safe while it was collecting that material.
Bennu's rocky surface presented a challenge for the original LiDAR-based approach to the touch-and-go sample acquisition event. As an alternative, the project developed an onboard optical-based approach called natural feature tracking. NFT requires detailed three-dimensional maps of the surface of Bennu. In order to build those three-dimensional maps, we need many, many images of particular patches of surface on Bennu itself.
And so all these surveys we've done throughout the mission have been at distances between several kilometers from the asteroid down to just a few hundred meters from the surface. And based on those different perspectives and what the shading of that terrain is, it's possible to build a 3D model. Very similar to how we have two eyes that allow us to have depth perception of what we see. NFT requires multiple features across the field of view to have a depth perception.
The original tag accuracy requirement was to touch the surface within a 50-meter diameter circle. Based on Bennu's rough surface, our actual performance has to be much better than that, at 10 meters or less. And even within that 10-meter area, there could be smaller localized hazards that may damage the spacecraft.
Right now, we are working on a flight software patch to help us avoid hazards as we come in for a sample event. When we do natural feature tracking, that is all autonomous on board the spacecraft, where we load the features or a catalog to the spacecraft, so we are telling it where we expect these features to be.
So as the spacecraft makes its progress down to taking the sample, we're recording images and then locating those landmarks to make sure we're on the right track. And if there's any issues with the trajectory or we see landmarks where we shouldn't, we know something's up and we can back away and wave off the attempt to try again.
As soon as we were dealing with that and processing the challenge that Bennu presented to us, we literally saw the surface explode, erupting particles into the near Bennu environment, and we panicked. And we thought maybe that this was a hazardous environment and the spacecraft was at risk and maybe the whole mission might be lost. And this is where we realized how the microgravity environment can really mess with your mind. What looked like a dynamic, energetic explosion on the surface was simply a little puff of material with flakes of the asteroid gently gliding around, sometimes going into orbit, re-landing on the surface of the asteroid. And it turned out to be an amazing science experiment. So what looked like a major catastrophe turned out to be a great opportunity.
As we were first approaching asteroid Bennu in that fall of 2018, in the December timeframe when we arrived, we could already clearly see there were a couple of interesting areas that, to be clear, none of the places looked smooth, but there were some areas that were a little bit smoother that we could actually see with our eyes just from that visual observation. But then we had to really study them in detail and quantitatively look at, is this possible to deliver the spacecraft? Is this going to be safe for the spacecraft? And are the particles small enough?
One of the most challenging aspects of pulling together that beautiful global mosaic of Bennu was getting the right data to make a mosaic. So before we even had the images that we stitched together, a few hundred in total, we had to make sure that we were taking images of the surface that were lit at just the right conditions so that you could see small shadows that would outline those particles, and also that were taken at sort of a straight on angle, or as straight on as we could do with our spacecraft, so that you didn't get a lot of distortion. Once we had all of that data, you're dealing with hundreds of images. All of these images have, 1 million pixels or more. It took a lot of effort, but it looks like a very seamless map of Bennu. It's also the finest spatial scale that we have ever mapped a planetary object, which is pretty impressive.
We went through a very rigorous sample site selection campaign, and we had 3 driving criteria. We had what we called the deliverability, which is how tight of a spot can we get that spacecraft into. We were looking at craters that were about 20 meters or 60 feet in diameter, just the size of a small parking lot, and the spacecraft's about the size of an SUV. So it was a really tight fit, especially compared to what we originally designed to. The second one was safety. Even if we could get into one of those tight spots, would the spacecraft survive? And we were particularly worried about tipping over and flying away into one of the many giant boulders that dominate the surface of the asteroid. And then the third one was sampleability. If we got the spacecraft there and it was safe, was there anything on the surface for us to pick up? We were looking for particles about 1 inch or 2 centimeters across or smaller. And there's very few patches of material like that on Bennu's surface. So we kind of evaluated all of that. In the background was a parameter we called science value. But the good news was everything on Bennu was scientifically valuable. We saw water-rich clay minerals, and we saw organic molecules, which are 2 of the prime types of material that we were trying to collect. So in the end, we kind of used the basketball tournament analogy, and we started with about 16 sites. We called them the Sweet 16, and we put them up against each other, and we evaluated how much fine-grained material we estimated was there. And we couldn't actually see the fine-grained material, but we could see where the big rocks were not, what we called the unresolved patches of the surface, and we assumed that there was fine particles there that we could pick up. We eliminated half down to the Elite 8 and down to the final 4. And when we had the final 4 sites, we performed a series of low-altitude reconnaissance passes to kind of do a safety check. And that very quickly revealed that 2 of the sites were quickly out of contention. One of them was simply just too small of a crater, and it looked a lot like one of the other sites, so we were able to eliminate it. And the second one looked really good. In fact, I thought it was the leading contender going into that phase, but it turned out to have a lot of fairly large rocks with the fine material interspersed in between it. And that one was gone, so we were down to 2. One we called Osprey, and one we called Nightingale. Both of them about 20 meter or 60 feet diameter craters. One near the equator, Osprey, one in the northern hemisphere, Nightingale. And it turned out to be kind of a contest. Osprey was safer, but Nightingale was more sampleable. And also the science looked better there. It was darker, redder, it looked fresh, like recently exposed, so not modified by the space environment. When we pulled the board, we had a site selection board, my heart kind of sank when Flight System and the Goddard Space Flight Safety engineers voted for Osprey, because I really wanted Nightingale. But the TAG-SAM team and the science team were voting for Nightingale, so it came down to me. I had to make the final decision.
Hello, and thank you for joining us in the booth here at AGU, the American Geophysical Union, for this special edition of NASA Science Live. Today we have a big announcement from the Osiris Rex mission. Osiris Rex is NASA's first mission to retrieve a sample of an asteroid and return it to Earth. And we're going to find out from where today.
So I stepped away from the meeting, I kind of walked out and I said, I have to go with the science, right? I have to go with the science, it's what we came here for.
Dante, do you want to tell us which one you've picked?
I will. So I'll say that just thinking that we're going to get this sample back to Earth sends chills down my spine. So the winner of the Osiris Rex Site Selection Championship is the Nightingale site.
All right. Make some noise, audience.
And I want the material from Nightingale almost like it was calling to me. So I made the final decision. We're going to go in. The safety was acceptable. Lockheed Martin agreed that they could sample that area, and the science is what made the decision.
It was a decision that had a lot of stakeholders, and a lot of people had to come together and make their case before a decision was eventually rendered by our principal investigator, Dante Lauretta. And so I remember during the sample site selection meeting, Dante turned to those of us who were scientists on the team and asked what our opinion was. And I think I was the first person who spoke, and I was just like, Nightingale. It has the organics, it looks fresh. Like, if we just put our science hats on, that is where the value is.
Nightingale and Osprey were always pretty high on the list, but in my mind it wasn't clear. We had some fascinating sites to choose some, including a few sites where they were very small sites, but it looked like there was some really fine-grained material there, but clearly they were just too hazardous for the spacecraft.
What is the biggest challenge of the site?
So the biggest challenge of the Nightingale site is those large boulders that are off on the eastern edge of the crater, because that tallest one, I colloquially call it Mount Doom because it has the classic kind of peak shape that we're familiar with from the literature. That's about 7 meters tall, and then when you're down at the bottom of the crater, that's another 3 meters. So we're talking 10 meters or 30 feet. So it's a substantial building-sized obstruction, and we're trying to get into a crater that's on the order of a few parking lot spaces wide. So we are doing a really tight job parking that, and we're aware that we have hazards around us. So precision navigation to that sampled material is our biggest challenge. So all we have left to do to deliver on our promise to the agency is get that sample safely back to the Earth, get it into our laboratories, and answer the fundamental questions about the formation of our solar system and why Earth is a habitable world.
Now, Osiris Rex is a one-of-a-kind spacecraft with an extraordinary team of engineers and scientists charting unexplored places. It was launched on September 8, 2016. The vehicle has traveled over 2.2 billion miles on a complex route to reach Bennu. You are here with us on a historic evening. It will be NASA's first sample return from an asteroid, the attempt to actually sample the asteroid Bennu.
OREX has descended below the 5-meter mark. The hazard map is go for tag. Contact expected in 50 seconds.
We're going in. We're going in.
This is a reality. We're actually going to be trying to sample on an asteroid.
This represents the hopes and dreams, hard work, blood, sweat, and tears of thousands and thousands of people who have worked on this program for over a decade to make this a reality.